Alright, in this video we will do some examples with multi-body systems. This is a multi-body system. You can tell because there's mass 1 and mass 2 both drawn into the system, so you're dealing with more than one object. Anytime you have more than one object specifically being asked about, then that's a multi-body system. In this problem, if we were just asking what's happening to mass 1 or just happening to mass 2, that would be different, but we're not. The question we're asking is for you to determine the tension in the rope that's between the masses if the system is in equilibrium, which means that there are forces acting on the body, or I guess more specifically, equilibrium means forces could be acting on the body, but the body is not accelerating. So you know that means the net force is zero because the acceleration is zero, and you know Newton's second law. We're also going to ask what the tension is that's holding up mass 2 if this system is in equilibrium. The reason that I am mentioning that this is a multi-body system, it doesn't seem like it is initially, but I could easily take this question and make it, I could place this whole situation in an elevator. And so that would be a situation where it's not in equilibrium and the motion of the two objects would still be related. The acceleration of the two objects, because they're tied to each other by taut ropes, the accelerations of the two would be the same. In this case, the acceleration of the two happens to be zero. Whether the acceleration is zero or not, you'll want to start with a free body diagram of each of the objects being asked about. So I want to draw a free body diagram of my bottom block. I know that the Earth is pulling gravitationally on the bottom block, and looking at the drawing I can see that there is a tension force pulling up on the bottom block. It is the tension of block 2 on block 1. I'd like to note that we know that these two are pointed in opposite directions, and we know that they are equal magnitude because we know that the net force is zero. It's not accelerating anywhere. However, if you start saying things like these two are equal and opposite, do not allow yourself to get tricked into thinking that that's because of Newton's third law. It's not. Newton's third law, as a reminder, tells us that every force on your free body diagram would appear on a different object's free body diagram, pointed the opposite direction. So these two happen to be equal and opposite because the acceleration is equal to zero, not because Newton's third law. Okay, let's take a look at the free body diagram for mass 2. Mass 2 has the Earth pulling down on it, and I drew that a little bit smaller and gave it a slightly different name because I don't want to accidentally mix up the force of gravity on mass 1 with the force of gravity on mass 2. They're definitely two different things. I also know that mass 2 has a tension force pulling down on it. You might call that the weight of mass 1, and I would not. And the reason I wouldn't do that is because what this is actually the tension force of mass 1 pulling on mass 2. I know that that is equal to the upward tension force on block 1 due to block 2. And when I say it's equal, what I mean is this is actually a Newton's third law scenario where these are the exact same interaction. So those two forces, the gold one and the green one, I put that hash mark between the two to indicate they're equal to each other. They're actually the exact same force. Now in this case, you could say that the tension pulling down on mass 2 is equal to the weight of mass 1, but that's only because mass 1 is not accelerating. If this whole situation were in an elevator and you were accelerating, for example, upward, then tension up on mass 1 would be more than the gravity pulling down on mass 1. That would mean that the tension pulling down on mass 2 would be more than the weight of mass 1. So I'm just suggesting that you might not want to get sloppy with saying things like the weight of mass 1 is pulling down on mass 2. That's, again, a really easy way to get yourself turned around by being a little sloppy with the terminology. Mass 2 I'm looking at has another tension force acting on it. That's what's holding it up. Mass 2 is being held up by the tension force between the ceiling and mass 2. And that has to be a larger force because it needs to be able to counteract not only the force of gravity pulling down on mass 2, but also the tension force pulling down on mass 2. Of course, if I were to look at this system and say, the tension from the ceiling rope down to mass 2 has to be strong enough to hold up mass 1 and mass 2 both, that would make sense. I could view these two as an individual block and just say that the rope that holds mass 1 and mass 2 together is an internal force. That's perfectly legitimate, and that's sort of what this video is getting into, is when do you really have to worry about that internal force, that tension between the two blocks? The answer is going to depend on what exactly you were asked in the question, actually. In order to calculate the tension force between the two blocks, I really only need to look at mass 1 and say that the net force on mass 1 is equal to the mass 1 times the acceleration of block 1, which we knew was 0. So the tension from 2 to 1 minus, because it's pointed downward, the force of gravity on block 1 equals 0, which means the tension on pulling upward on block 1 is equal to m1g. And if we had numbers for the masses, we could plug that in and calculate how strong that tension is. So in order to calculate that tension, I do have to evaluate one of the blocks individually, mass 1 being the best one here. I couldn't determine that tension force if I tried to treat mass 1 and mass 2 like a single object and just say, oh, and they happen to be tied together. But if I were asked only about the other one, I might be able, the rope holding mass 2 up, I might be able to just combine the two masses. And you'll see what I mean when I say that F net equals ma on block 2, and the net force on block 2 is the upward tension from the ceiling on 2 minus the force of gravity pulling down on 2 minus the force of tension from 1 to 2. And again, those other two are minus because they're pointed in a negative y direction. That whole thing equals 0 because the acceleration of block 2 is 0. And so now I can calculate that the force of tension from the ceiling to 2 is equal to the gravitational force on block 2 plus the tension force of 1 to 2. And we know that the tension force of 1 on 2 in this case, we just solved on the other side there, is equal to mass 1 times g. Of course, the gravitational force on mass 2 is mass 2 times g. So we could say the tension force is equal to the combined masses times g. So again, to determine the tension force between the two blocks, I need to analyze the blocks individually. But to determine the tension force that is holding up the system of blocks, I don't. I could analyze the two blocks as a single system of mass 1 and 2, and you would have gotten this exact same answer, parentheses mass 1 plus 2 times g. That may seem like an overcomplication, and in this scenario it sort of is because it's not accelerating. So we'll take a look at a situation where it's accelerating, and I'll show you why this is advantageous. Alright, here we have 3 blocks on a frictionless table. The masses are given, mass 10 kilograms, 20 kilograms, and 30 kilograms. And you're being asked to determine the acceleration of the system shown, and then the force of contact between B and C and the force of contact between A and B. Let's go back to that first question, though, the acceleration of the system shown. The force of gravity is pulling down on each of these, and they're resting on a surface, so a normal force is pushing up on each of these, and the only force that's going to accelerate any of them is that 15 newtons. But that 15 newtons is only acting on block A. So the question of how you could possibly determine the acceleration of B and C is a little difficult to analyze with the type of analysis we've been doing up till now. A useful problem-solving strategy when you have two objects that are either in contact with each other or are tied to each other through some sort of rope or string or something like that. Do the objects have the exact same motion? If the objects in this system, the multiple objects, will all have the same acceleration, then you might be able to, at least for part of the problem, treat them as a single object. Much like if you were to calculate the motion of a person who is jumping off of a diving board into the water. You don't need to calculate the acceleration of their foot separate from their torso, separate from their head. They're all one object accelerating at the same time. There are other times where you might want to analyze the individual body parts differently because you're talking about a person who is doing some sort of twisting and turning and so forth in their dive. In this case, we're not talking about anything like that. We're just talking about objects A, B, and C all accelerating. I can tell by looking at the drawing, they're going to accelerate to the right. But how much they accelerate means I have to account for all of the masses. I want to ignore the fact that A touches B and B touches C and that they're all separate objects. I want to assume that this is just one object, and that one object is box A plus box B plus box C. Its masses of 10 kilograms, 20 kilograms, and 30 kilograms all together for a total of 60 kilograms. This allows me to then say that the problem is very easy to determine the acceleration at least. The net force will be in the x direction, the acceleration will be in the x direction. The net force is given as 15 newtons. The net mass, or the total mass, is 60 kilograms. And so the acceleration is 0.25 meters per second to the right. That was really easy to do. Once I've done that, I can establish very explicitly that the acceleration of box A is 0.25 meters per second to the right. And the acceleration of box B is also that much. And the acceleration of box C is also that much. So analyzing it all at once allows me to then take that value of the acceleration and go in and analyze the individual boxes whose accelerations I know. I know the acceleration of box C is 0.25 meters per second. I also know that a free body diagram of box C looks like this. The gravitational force pulls down, the normal force holds it up. Those two add up to zero acceleration in the y direction, zero net force in the y direction. The only thing accelerating box C is that box B is pushing it. The net force on box C is equal to the mass of box C times the acceleration of box C. The force accelerating box C is box B pushing it. And the mass of box C was given as 30 kilograms. The acceleration we just determined of the whole system is 0.25 meters per second. So that means I can determine one of the questions that I was initially asked. What is the force between box B and box C? Box B is pushing box C to the right, 7.5 newtons. It has to be, because that's what is necessary to make box C accelerate at the 0.25 meters per second that we know the whole system is accelerating. I can then say box B, whose acceleration is known, has a free body diagram that looks like this. The force of gravity down and the normal force up are equal to each other. So a net force of 0 in the y direction and an acceleration of 0 in the y direction. But the box is accelerating to the right. So I have a force pushing it to the right, A pushing on B, that is larger than the force pushing to the left, box C pushing on B. But remember, by Newton's third law, box C pushing on B is the same as box B pushing on C that we just calculated. That's why I left them the same color. The net force on box B is equal to the mass of box B times the acceleration of box B. The net force on box B is A is pushing B to the right minus C, which is pushing B to the left, and the mass is given 20 kilograms. We just found the force between B and C is 7.5 newtons. From the perspective of box C, that was positive, but from the perspective of box B, that's negative because it's to the left. Therefore, the force with which box A is pushing on box B is 12.5 newtons in a positive direction. Notice that's more than the 7.5 newtons that was pushing on box C, so that's a nice little check on my math. If I calculated something smaller than 7.5 newtons here after my free body diagram said that the force to the right should be bigger, then that would be a good sign that I did something wrong. Let's take a look at box A here. Box A has gravitational force and a normal force also that we know will add up to 0 net force in the y direction. We know that box A interacts with box B, so it has that interaction force B on A. We also know that there's 15 newtons given to us pushing to the right on box A. If I go through and double check things with Newton's second law here, I will get that there's 15 newtons to the right minus the interaction between B and A, which we just calculated was 12.5 newtons. That will equal the mass of box A times the acceleration of box A. And if we go through and check this math, we get on the left 2.5 newtons and on the right 2.5 newtons. We didn't need to double check that. It was just worth making sure that we're doing the math correctly. So again, my point with this is that I can treat A, B, and C like a single entity, a single unit for some of the calculations, and other times I can't. When I can't is mostly when I am explicitly asked about the forces that are acting between box A and B, or box B and C. When I'm just asked about the acceleration of the system, and I know that all parts of the system accelerate together, then I can treat it all as one system.